So all of you could join, right? Like the course, the global plus one. Okay. So, uh, so we were looking at Büchi automata. So what is the Büchi automata? So these are automata which accept infinite words, right? So they read infinite words, and so there's a finite alphabet. And what was the acceptance condition? Like, so there are some notions of good states, and these good states need to be visited infinitely often, right? So we defined something called, if there is a run for a given word, we define something called inf of R, which is like the set of states which are visited infinitely often in the run. And then alpha is a set of states again, right? And then if the intersection of these set of states which are visited infinitely often, the intersection of this with alpha is non-empty, then the run is an accepting run. Right? So this is what I thought. And we also say like what are omega regular languages? These are omega. This is so essentially, if for a language over omega words, if there exists a non-deterministic Bushy word automaton which accepts that language, then this is an omega regular language, right? So we showed some examples like infinitely many years. So this is the automaton which accepts infinitely many years because so the alphabet is AB. And now you see that when you are having infinitely many years, they will be visiting this state, right? So this is my alpha. So this was my alpha. So this particular state will be visited infinitely often. And hence, this automaton accepts infinitely many years, right? This Bushy automaton accepts. And this is a deterministic Bushy word automaton. We write W for words. And whereas if we consider the complement of this language, which is like finitely many years, then we have a corresponding non-deterministic Bushy word automaton. And what we sort of like, we did not have a formal proof yet, but we also say that there doesn't exist a DBW for finitely many to accept this language. So deterministic Bushy word automata are strictly less powerful, less expressive than non-deterministic Bushy word automata. So this is what we discussed. And yeah, so we also started looking at the closure properties. So we started with the union of non-deterministic Bushy word automaton. They are just like you put the two non-deterministic automata side by side, and that's what gives in the union. Okay, for non-deterministic Bushy word automaton. And what about intersection? Like, so in intersection, it's like you have to have for example, it should accept the words which are in both the languages. Right? So the usual way one would do for automata over finite words is that you do a product construction, and then you say that if both the like automata, the product automaton reaches a state which corresponds to the final states of both, then that is kind of like an accepting state. But then we saw that that simple construction doesn't work here. So this was this example, and if you take the product, like you get something like this, which doesn't have any accepting state at all, right? So if you just, so S1 and S1 is the starting state, T1 is one accept state, like belongs to alpha 1, S2 is some starting state, T2 belongs to alpha 2, and both the automata, they accept, like both this one as well as this one, they accept A omega. So if you take their intersection, you should get something like the product should also accept A omega, right? But here it's not the case because like the standard thing is like we say that it's alpha 1 cross alpha 2. So those should be my alpha in the product automata. Now here, none of these states S1, S2 as well as T1, T2, none of them are belong to the alpha. Hence, this does not. So that this accepts the empty language. So the standard product construction doesn't work. So what we say is like you have to have two copies. In the first copy, you look for the alpha 1. Once you see alpha 1, you go to the second copy and then you come back again. So this alternation will happen. And my final thing will be in the first copy, you have the alpha 1, then followed by Q2 times Q2 times 0 in the first copy, right? First copy acceptance, the set of accepting states or the good states, that gives you the alpha. Okay, so we discuss this, and then so we also saw that this product, like this specific construction we had, this does not introduce any non-determinism. So DBW are also closed under intersection. And are DBW closed under union? So that we also say it's true because you can just have the standard product construction. You don't need even these two copies. The standard product construction should work for union. So DBW are closed under union. Then for complementation, DBW are not closed under complementation because we saw that language that it has infinitely many A's, and this is of course accepted by a DBW. This DBW which we saw a bit earlier, and then if you consider the complement language, then it's like finitely many, right? So finitely many A's, and we kind of we did not formally prove, but we sort of argued that finitely many A's there doesn't exist a DBW. Hence, DBW are not closed under complementation. But what we also showed is that you can construct, given a DBW, you can construct an NBW which will accept the complement of the language, right? So given a DBW, you can always construct an NBW which will accept the complement of that DBW language. And again, like the idea was that you have two copies, and in the first copy you have all the states, and then non-deterministically you sort of guess that when you will move from the first copy to the second copy, and in the second copy you don't have any of the alpha states, right? So this was the idea. So now we say that we will be working with the complementation for NB complementation for NBW. And what we are going to show is that NBW are also, I mean, NBW are indeed closed under complementation, unlike DBW. Non-deterministic Büchi word, they are closed under complementation. So so far so good. Like, any question from anybody among the online participants? Okay. So so for the complementation procedure, this is what we discussed, that Büchi himself provided a complementation procedure which gave a W exponential blow up. Then like 25 years later, Prasad Sispla and I think Pulpar and Vardy maybe, so they gave this construction which has like 2 raised to order n square. Then an optimal construction was, why we say optimal, that we'll see later. There's an optimal construction for determinization. So this was given by Safra, which has 2 raised to order n log n. But this kind of like, it's a determinization construction, but we know that NBW cannot be determinized, right? So you need some other acceptance condition. So it's called a deterministic Rabin word automaton. We'll see what a Rabin acceptance condition is. And then there are some other works, like, so the one that we are going to look at, so this work is about progress measure. And then there was this work by Kupferman-Vardy, which uses ranks that is also similar to progress measure. And it uses alternating Ko-Büchi automata, but we are going to look at a modified that Kupferman-Vardy construction, which will kind of bypass the Ko-Büchi, alternating Ko-Büchi part. So we do a direct kind of a construction, right? So as I mentioned that these first few lectures that we are going to have, maybe like almost maybe let's say 1/3 of the course, we are going to sort of follow this chapter by Orla Kupferman, who actually suggested this, one of the contributors to this algorithm that we are going to look at. So there is this book called Handbook of Model Checking. So there is this chapter which she wrote, and that's what we are going to follow. And I think in the Google Classroom, so I have put it like the link to this chapter. Okay. So what is the idea? So we were going to look at, for example, a graph, okay, a run DAG, like a directed acyclic graph, which kind of captures, like, given a word and the automaton, it's going to capture all the runs of the automaton corresponding to this word. Okay. So let's see how this DAG is constructed. So you have this automaton NBW A, and let's say the number of states is n, right? Small n. And let's say the word W is of this form, A1, A2, etc. This is an infinite word, and we are going to construct an infinite DAG, right? Which will consist of all runs of A on W. So the graph is of the form V, E, right? It's you have a set of vertices, you have a set of edges, and the vertices are of the form, it's a subset of Q cross N, right? So what does this N denote, or what does it, where does it come from? It gives you the levels, like you start from level 0, level 1, level 2. You start from the set of initial state, then you read a letter, which is say A1, then you come to the next level, which is level 1. Then you read another letter, level 3, like that, okay? So, so the union, like, so essentially this V is the union of QL. QL is the set of states that you have in level L, and this is the level number, okay? And how do you get QL plus 1? So it's the union over, like, so delta of Q comma AL plus 1, since it's a non-deterministic Büchi word automaton, you get a set of states, right? So from some state, let's say you have this level L, you have a state say QL, you may go to a bunch of states when you are reading AL plus 1, right? And you go to get some set of states, and you do this for every such state in level L, and you take their union to get the set of states in level 1. Clear? So this is the thing, and the set of edges, as you can see, it's like there is like E of QL to Q prime L plus 1. You have such an edge if Q prime belongs to delta of Q AL plus 1, right? So you have, just as I showed here, so you have like something from here to here, there is an edge. If from this particular state, by reading this letter, you can go to this next step, and then you are going to the next level. So you have this. So now one thing, since it's a directed acyclic graph, one thing which is very easy to see is that at any level, there are at most n vertices, right? So it's not too difficult to see. And QL, we call, so this is the definition. So we'll say QL is an alpha vertex if the state Q belongs to alpha. Clear? So this is an alpha vertex if the state belongs to alpha. And now G is an accepting run DAG, right? G is an accepting run DAG if G has a path with infinitely many alpha vertices. Okay, so it's an accepting DAG if there is a path with infinitely many alpha vertices, right? So it's an infinite DAG. There are infinitely many levels, and it's accepting if it has infinitely many alpha vertices, otherwise it's rejecting. Okay, and the automaton accepts the word W if and only if G is active. Clear enough? So you have, as long as you have one infinite path, since it's a non-deterministic Büchi word automaton, it should be able to accept the word, right? So one such path which will visit the infinitely many alpha vertices, it corresponds to an accepting run, right? And it's rejecting if you don't have any such infinite path which will have infinitely many alpha vertices. Clear? Right. And then we also think that, so this graph is infinite, right? Even if it happens that in this graph, in this DAG, you have like infinitely many alpha vertices which are appearing in the DAG, that does not necessarily imply that the DAG is accepting, right? It accepts the corresponding word. Why is it so? Because you can have infinitely many runs, and each run visits an alpha vertex only finite long. Clear? So we saw this example, like you have infinitely many runs, but now every run would visit, say this, I mean, like every run would visit this alpha vertex Q1 at most once, right? So that, okay. So far, so good. And now what is the thing that we are going to do? We are going to show that NBW are closed under complementation. So we are going to do the complementation construction. And so first we'll do a bunch of like definitions, and then we'll try to get to the construction, okay?
What does that diagram earlier in the earlier slide mean? The last one?
Okay, so here essentially, like you mean this diagram, right? This diagram?
Yes.
Yeah. So what this diagram does is essentially like you see that I have a run which will go from Q0 to Q1 to Q2 and stays in Q, right? So this Q1, this is an accepting like an alpha state, alpha vertex, right? Similarly, you can have a run which will take once this thing and then go take this, right? So it will go along this and then take this. So this is one alpha vertex, right? This run visits the alpha vertex once. Then you can have like take the loop over Q0 twice and then come to Q1 like this. So all I'm saying is
Okay.
like you have infinitely many levels and you can have one run where in each level you find some that Q1 appears. Okay. At each level, you
Okay.
find that Q1 is appearing corresponding to one run. But so what happens is that in this run DAG, Q1 appears infinitely many times, but none of the run has Q1 appearing infinitely many times in it. So in the run DAG, Q1 appears infinitely many times. At each level, you can have like a corresponding to each level, you can have a run where Q1 will appear, but none of the runs will have Q1 more than once individually.
And the DAG represents all possible runs, right? Not just a subset of runs.
All possible runs, yeah.
Okay.
Okay, yeah. And at any level, you are not going to have, that's why more than n states in the tag. Clear? Okay, good. So now let's say, yeah. So I'm going to define a ranking function. So what is the idea of the ranking function? So we will say that, so we will start with some rank, okay, from the initial level, and the rank will gradually slowly decrease. And we'll say that, we'll see that some finite number of ranks would suffice. Okay, the rank would gradually decrease. And we'll sort of show that we'll start with an initial rank and it will be non-increasing. At some point of time, the rank will get stuck, right? And so the thing is that so I'm going to define the ranking function, its properties. We'll say that this ranking function f, it's an odd ranking if all the paths of G eventually they get trapped in an odd rank. Okay, if all of them they get trapped in an odd rank. So yeah, I mean, please stop me if you have questions. So some of the definitions I thought I would just write down rather than writing because I was getting a bit slowed down. So I thought I would just write some of them. Yeah, okay. So now, for example, like, so what is this F? So for all the V is the set of vertices in the graph, right? In the DAG. And you have like, so I'm giving every vertex a rank which is from 0 to 2. Okay. Now, what about so there are two properties of the ranking function that we find. So one is that the alpha vertices get even ranking. Okay. So if for a vertex QL, right, if f of QL is odd, then we know that it is not an alpha vertex. So this is one of the properties. And what is the other property? So it is monotonically non-increasing random one. So what does it mean? That for all edges QL and Q prime, QL, Q prime, L prime, right? So if there is an edge from QL to Q prime, L prime, then f of Q prime, L prime should be less than equal to f of Q prime. Clear? So this is monotonically non-increasing. Now, just, yeah, so note that like whatever I'm starting with, so I'm starting with some 2n, right, a finite number. Now, each path in G eventually gets trapped in some rank. Clear enough? Right? Because it cannot decrease arbitrarily. Right? Each path, if you consider each path, it will eventually get trapped in some rank. Now, what I'm saying again in the definition, it says that F is odd ranking. F is an odd ranking. Okay, if all the paths of G eventually gets trapped in an odd rank. Clear? So if all the paths.
By trap, we mean we can't.
You cannot reduce further. So formally, exactly. So this is what it says, that formally I'm saying that if is odd, like if you see this, I think it will be clear. It means that for all paths like this, there is a J. For every path, there is a J such that this is odd, right? Such that Qj, so for every such path, right, there is a J such that f of Qj comma J is odd, and for every subsequent states that appear in the subsequent levels, they have the same rank. Clear? So when I say it gets trapped, it means that you are going sort of like going down, and at some point of time, the rank does not reduce further. Okay, if it's an odd ranking, if all the paths have the get trapped in an odd. Clear? Good. So there are two things to then again note here, that when we are defining the ranking function, then there are two sort of like properties. One is that alpha vertices get even ranking, and the vertices, they are getting monotonically non-increasing ranks around path. Okay, so these are the two properties of the ranking function. The way we are using. Okay. So now what we are going to do is that we will show that G is rejecting, right? So what is the definition of G being rejecting? What was the definition of G being rejecting? Right. So all the paths should not like visit, I mean, any of the path. It's accepting if there exists some path which will visit alpha infinity often, and it's rejecting if for all the paths they don't visit alpha infinity often, right? And so we are saying that G is rejecting if and only if it is an odd rank. And what was the definition of the odd ranking? That is true. So that is anyway.
It has
The value, like it gets trapped, all the runs would get trapped in an odd rank. Yeah.
Sir, we are not not all graphs would have a ranking.
So that's what we are going to show, that, for example, like if a word, for example, is going to be rejected, then I construct the DAG and I am going to find an odd ranking function for it.
So we are not saying that every such automata is going to have a rank.
So the thing is that if you consider a word, right, either it's going to be rejecting or it's going to be accepting, right? Corresponding to the run, I will be able to define a ranking function. Okay, I'm going to define a ranking function. Now, depending on whether the word is going to be accepted or rejected, we'll see that whether I can get an odd ranking function or not.
Sir, but then, like, suppose a word is accepting,
Yeah.
then won't it be kind of oscillating between odd and even? And at each point, it should keep reducing, right? But that will kind of.
It might get stuck at the.
It might
That is
get-
a possibility, but
Yeah.
if it's oscillating between odd and even,
Right.
then won't such.
No. So the thing is that, like, what am I saying? That the alpha vertices will always get even rank.
And not
The alpha-
always.
No, that I'm not saying.
Okay.
Okay. So the only thing that I'm saying that the alpha vertices should get even rank.
Okay, then I.
Okay. Yeah. Good. Thanks. Any other question? So now, so this is what we are going to state is that, or show is that G is rejecting if and only if it has an order. So I think this is pretty much, it's going to take almost the whole of today's lecture. So one direction is easy. Which direction is easy? So G is rejecting
Odd ranking implies reducing.
If it is odd ranking, then it's going to be rejected, right? If it is odd ranking, then it is why?
Because then after a point there are no alpha vertices.
Exactly.
And
So it gets stuck
it has finite.
it gets stuck in an odd rank, and we know that the alpha vertices should get even rank, right? So which means that if you get to see only odd ranks, so that means that none of the alpha vertices are appearing in all the ranks, right? So this direction is easy. So if so then which, okay, so let me write odd ranking implies that G is rejected. Okay, so this direction is understood. Now we are going to look at the other direction. So which is the more difficult direction, which is that if G is rejecting, then G has an odd ranking. Okay, so what does it require? So we have to sort of construct such a ranking function, right? How we will construct the ranking function, that is. And the idea, so finally what we are going to do again, what is the idea of all these things? What are we trying to do? So we are going to construct a non-deterministic keyword automaton, which will accept the complement language, right? That is our final goal, right? So the broad idea is the following, that the complement automaton will sort of like guess, it's a non-deterministic Büchi word automaton, right? The complement language is also a non-deterministic Büchi word automaton. So the complement automaton will guess such a ranking function, which is an odd ranking function. Okay, and it will also keep track of the states for which will have kind of even ranks, and then we would like to see that those even, like the set of states with the even ranks, that will become like an empty set and so on, right? So if I have an odd ranking function and the set of states which have even rank, that becomes an empty set, and if we can visit this thing infinitely often, that will essentially ensure that this word is not accepted in the original automaton. Is it clear, like what we are trying to say? I think it will become clearer. I mean, I just gave a very broad intuition, but like I think we'll look at the construction. Okay, so essentially this non-deterministic Büchi word automaton, which is the complement automaton, it will try to keep sort of guess such an odd ranking function. Okay, so the state space of this complement automaton will be over all these different ranking functions. Okay, different odd ranking functions. Okay, good. So now, given that I have said this, you can try to think what should be the size of this complement automaton, right? The state space, as I said, it will keep track of like the different odd ranking functions themselves. So now you can think of how many such functions are possible, right? And that should give you the size of the state space. Clear? Okay. So now let's try to first look at this direction. It is if G is rejecting, then G has an odd ranking. So again, some definitions we'll start with. So we say that a vertex is finite. Okay, a vertex is finite in a DAG, G prime, which can be a subset of G, if only finitely many vertices are reachable from QL in G prime. So a vertex QL is finite in G prime, which is a subset of G. I mean, it is like a subgraph of G, if only finitely many vertices are reachable from that. Okay, and I say that this vertex is alpha free in G prime if and only if all the vertices in G prime that are reachable from QL are not alpha vertices. Okay, it is alpha free. So I'm saying alpha free if everything that is reachable, right? In general, it may be possible that there are infinitely many vertices which are reachable from a particular vertex. So I'm saying that this vertex is alpha free if all these vertices that are reachable, they are not alpha vertices. And in particular, we can also say that an alpha free vertex is not an alpha vertex, right? An alpha free vertex should not be an alpha vertex, right? I mean, the assumption is that something is always reachable from itself, okay? So an alpha free vertex cannot be an alpha vertex. Now we are defining an infinite sequence. We are defining an infinite sequence of DAGs like this. Inductive, we are defining. So how are we defining? We are saying that initially G0 equal to G. So G0 equal to G, and for every I, we are saying that G2I plus 1. Okay, so this is an odd subgraph. So we are getting this by removing some vertices from G2I. Which vertices we are removing from G2I? The vertices which are finite in G2I. Okay, so I'm just inductively constructing some sub DAGs, right? So initially I have the whole G0 is the whole G. Then I'm saying that, well, if I have to construct G1, then look at the vertices in G0 which are finite. That means only finitely many vertices are reachable from those vertices. So I get rid of those vertices. I get G1. Now from G1 to G2, what I will do? I will see what are the vertices which are alpha free in G1. Okay, what are the vertices which are alpha free in G1? So what was alpha free again? So these are those vertices from which you cannot reach any alpha vertex, right? All the vertices that are reachable from such vertices, they are not alpha vertices. So they are alpha free vertices. I'm going to remove those ones in the next, right? And this will do. Okay, good. Now the question is that, like, one thing we might ask, that how long we will need to do G0, G1, like is it going to continue forever, or are we going to stop at some time, right? So this is what we see. Okay, when we are going to stop? Okay, so in order to understand this, so I mean I already told you that the broad idea of the complementation construction. So the state space it's going to have, it's kind of going to non-deterministically guess all these functions, right? All these ranking functions, right? So that's the state space essentially, along with some of the subsets, like which still have even rank, and they should. So if there is an even rank, it means that you have visited some alpha vertex, and eventually you would not like to visit those alpha vertex, right? So those states should disappear from that set, right? So now I'm saying that if so, any question from the online participants or anybody? Like so far, it is clear. It's clear so far, right? So now I'm saying that let's consider this lemma. So what I was saying, that I have these G0, G1, G2, etc. So how long do I need to construct such subtypes, right? So if G is rejecting, so this is what the lemma states. If G is rejecting, then for every I greater than or equal to 0, for every natural number I, you consider this graph G2I, right? So G2I, this one. So in G2I, there exists a level Li. Clear? So what I'm saying, in G2I, there exists a level Li such that for all L greater than or equal to Li, for every level, so in G2I, there exists a level Li. For all L greater than or equal to Li, there exists at most n minus I vertices at level L. Clear? So what are the quantifications? I'm saying for all I, consider the G2I, the even number of that, right? So in that, for all I, there exists an Li, right? Such that for all L greater than or equal to I, right? At level L, there are at most n minus I such n minus I vertices. Clear? So the statement of the lemma is clear. Okay, good. So now how are we going to prove this? As usual, like we'll prove by induction on I. So is it true for the base case? Is it true for the base case? It's easy to see that the base case. Why is it so? Sorry?
2i is still a zero. It's the graph.
Yeah, it's the graph itself. And why it's n minus y I in the graph? It's just n, right? N minus 0 is n, right? And we know that in a graph at any level you cannot have more than n vertices, right? So it's true for I equal to 0, right? So now let's consider the induction state. Suppose it's true for I, right? So it's this thing holds in G2I. We are going to show that it holds in G of 2I plus 1. You are going to have, so in G2I plus 1, there exists some level Li plus 1, such that for all L greater than equal to that level Li plus 1, you have at most how many? N minus I plus 1 vertices. Clear? This is what we are going to show. So just consider now two cases. Suppose G2I is finite. If G2I is finite, if the graph itself is finite, then G2I plus 1 is going to be empty. Clear? It's going to be empty because how we construct G2I plus 1, if you recall, we are removing all the finite vertices from G2I. If the graph itself is finite, every vertex is finite, you remove everything. So you get an empty G2I plus 1. Okay. And if G2I plus 1 is empty, then G2I plus 2 is also going to be empty, and so we are good. Okay. What if G2I is infinite? What if G2I is infinite, right? So then the claim is G2I plus 1 contains an alpha free vertex. So this is the claim which we are going to show, right? So again, so suppose if we have this claim, then can you tell me how, or what I'm trying to ask you is that, can you suggest how does this claim help? How does this claim help? If I prove this, then how will it help? It contains an alpha free vertex.
We just had to remove one vertex more by the induction step where
Yeah.
already we had n minus
I,
and now we are removing one more, so that will be this clear.
yeah, but I also have to say, like, every level after that, right? That should also have one less. It's not only this one level should have one less. So what is the definition of alpha free?
All the parts which go from there are outside.
Right. So no alpha vertex is reachable. So if you find some alpha free vertex, that means the things that you are reaching, they are also alpha. Right. So that's the thing. I mean, so you get the intuition now, right? So that's how this claim is. So once you, and then as you say, like once you remove that one vertex, it's going to reduce by 1. It was n minus 1, now it's going to be n minus I minus 1. So, right? So, so we need to prove this claim, right? So, now let's see. So this is what we are going to show, that G2I plus 1 contains an alpha free vertex. So we are going to prove by contradiction that suppose G is rejecting, right? So we already start with the lemma is like if G is rejecting, then this thing is equal. So I'm saying that suppose G is rejecting and none of the vertices in G2I plus 1 is alpha free. Okay. So now one thing we should note is that G2I plus 1 is infinite. Why? Because G2I is infinite, and from G2I to G2I plus 1, how do we get? How do we obtain? So how do we reach? How do we get this? How do we say that G? So, okay, so how are we proving? So we say that We are now going to prove the induction state. So we already proved the base case. This is done. Now we are going to prove it for this arbitrary I. If G2I is finite, then we showed that this is fine. If it is not finite, if it is infinite, then my claim is that G2I plus 1 is also infinite. Why? Why?
We have just removed the finite vertices.
Correct.
Suppose G2I plus 1 ended up having then we should have technically removed that as well.
Exactly. Right? Is it clear? So how, okay, so let's see just again how we constructed this. So G2I plus 1 we are getting by removing the finite vertices. Finite vertices means that from a vertex you only reach finitely many vertices. Right? Is it okay? So are you convinced that if G2I is infinite, then G2I plus 1 is also infinite?
Yeah.
Is it, or any question, or do you think it's not, I mean, it's getting difficult to follow, right? Because what am I saying? I'm saying that from G2I, so suppose I have G2I, okay, I remove the finite vertices. Remove finite vertices. Right? Now, suppose G2I is infinite. Okay? G2I is infinite. Now, removing the finite vertices means that you are removing those vertices from which only finitely many vertices are reachable. It's a connected graph, right? Only finitely many vertices are reachable. Now, this is an infinite graph. So, which means that from the vertices here, there are infinitely, like there exists such a vertex from which infinitely many vertices are reachable, right? It's an infinite graph. So there should exist a vertex from which infinitely many vertices should be reachable. So if you remove the finite vertices from that, you will still be, I mean, you will still have a graph from and with vertices from which infinitely many vertices will be reachable, right? If G2I is infinite, then G2I plus 1 is also infinite. Clear? Any question? Okay, this is fine. Okay. And the other thing is that every vertex, I have removed the finite vertices. So now I have only those vertices from which infinitely many vertices are reachable. Right? Those vertices from which infinitely many G2I plus 1. From every vertex, there are infinitely many vertices which are reachable. Otherwise, they would have been removed in this state from G2I to G2I plus 1. So every vertex in G2I plus 1 has a successor. Clear? So every vertex in G2I plus 1 has a successor. So now I want to prove that so there exists to show there exists a vertex QL that is alpha free. Okay, in G2I plus 1. Okay, so how do I show this? How do I show this?
Suppose that none of the vertices are alpha free, that means from pick any vertex, from that there will be a path which eventually goes to another alpha vertex. Then that vertex is also not alpha free. So, oh, but it's an alpha vertex.
But then it has a successor.
Take its successor.
And then you can
And
go for the next
that
alpha.
is not alpha free, so we can go ahead. So it will be infinitely many.
And hence
And then
there's a path which has there's an accepting path. Very nice. Clear? So we prove by contradiction. So suppose, so we are proving by contradiction, right? So suppose G is rejecting, none of the vertices is alpha free. So which means that from every vertex, so that means from every vertex, so this is what it gives us, right? From every vertex, and alpha vertex is reachable. Right? So now you consider a vertex, let's say QL, you consider some vertex QL, and from QL, you reach some vertex, which is an alpha vertex, say Q1, L1, right? So this is an alpha vertex. Now you consider, so this is an alpha vertex, right? So that means Q1 belongs to alpha. That's what it means. Now, what do we know? Every vertex has a successor, right? We saw that. So now you consider the successor of this, Q1 prime, L1, right? And from here, an alpha vertex is reachable. So you go to Q2, L2, correct? And then there is a successor Q2 prime, L2 prime, right? So you can just do this forever and get an infinite path which will have infinitely many alpha vertices, and that contradicts with the fact that G is rejecting, right? There is an infinite path which visits infinitely many alpha vertices, and it contradicts with the fact that G is rejecting. Clear? Okay. So, right. So now the remaining part, I think we already mentioned, right? So, so then what do we get? Like suppose QL is such an alpha vertex, alpha pre-vertex in G2I plus 1. Clear? So QL, so we say, what was the claim? The claim was that G2I plus 1 contains an alpha free vertex. So suppose QL is such an alpha free vertex. We get that. Now, suppose QL is such an alpha free vertex in G2I plus 1. Now, we know that there are infinitely many vertices that are reachable from QL in G2I plus 1. Why infinitely many vertices are reachable? Because whatever vertex is there in G2I plus 1, from every such vertex, there are infinitely many such vertices reachable. Otherwise, they would have been removed in that while you were constructing G2I plus 1 from G2I. Right? And since this is alpha free, all the vertices that are reachable, they are alpha free. Right? So what do you have? You have like an infinitely many. So there is a vertex QL. From QL, there are infinitely many such vertices which are reachable that are alpha. Right? So, do you know what is Koenig's lemma? So, do you know what is Koenig's lemma? So, you have heard of it. Okay, so sure, of course, I'm going to say that. Does anybody want to say among the online participants what is Koenig's lemma? I'm pretty sure some of you have seen. Among the online participants, what is Koenig's lemma? Somebody can help me, maybe. Does someone want to help me with the Koenig's lemma? Nobody? Yeah. Yeah, one of you can unmute yourself and tell me. Okay.
It's about infinite paths.
Right.
I don't remember the exact ones.
Okay. So the idea is the following: that if you have an infinite graph, okay, if you have an infinite graph with which has like a finite degree, so that means from every vertex only you have finitely many successors. Okay, and you have like from from one vertex to another vertex that can be connected. It's called locally finite. Essentially, you can have one vertex to another vertex, which is connected by finite number of edges. Okay. Then what you have is like there is an infinite path. So you have an infinite graph. You have finite degree, right? Then there is an infinite path in the graph you can find. Clear? So there is an infinite path. So now how we are using this Koning's lemma? We are saying that, well, there is a vertex from which is alpha free. The vertices, there are infinitely many vertices which are reachable from that. They are also alpha free. And hence I have an infinite, and also the degree is finite because the degree comes from the delta function, right? Which are my successors. The degree is finite. It's an infinite graph with finite degree. And that gives me and infinitely many vertices are reachable from QL. That gives me by Koning's lemma that there exists an infinite path starting from QL. And since QL is alpha free, all the vertices which appear in this infinite path, that is alpha free also, right? So now then I'm saying that suppose this is the level is this N here, right? And all the vertices are alpha free. So I can get rid of that alpha free vertices, right? As we were discussing. And then beyond level L, we are going to get, I mean, more specifically, I should set my Li plus 1, Li plus 1 to be max of Li and L. Max of Li and L. Okay. And beyond that Li plus 1, if I get rid of those alpha free vertices, then in G 2I plus 2, right? Beyond this Li, I mean, from the level Li plus 1 and beyond, I am going to get at most n minus I plus 1 vertices in each level. Okay, L in each level L greater than equal to L plus 1. Clear? Okay, good. So what is the corollary of this? Can we say this? Is it easy to see that in G2n there are finitely many vertices now? In G2n there are finitely many vertices. Is it easy to see, or why is it true? So I made this statement. So okay, let's go back to the, I think we should look at the corollary statement again. So in G2i, beyond a certain level, right, you have at most n minus I vertices.
So then I is N.
I is n, then beyond a certain level, you have 0 vertices. So you have vertices only up to a certain level, that level ln, right? Hence, G2n is, and if G2n is finite, then G2n plus 1 is n. Okay. So in fact, if we keep on doing this construction, we don't need to do it for too long, right? We can just get after a while, we are going to get this subdax, it will become clear. So far, so good. Okay. Now, yeah. So now we'll look at this main lemma, which we started with sort of, and this is going to use this corollary, okay? That G2n plus 1 is empty, G2n will have finitely many vertices, and G2n plus 1 is empty, and so on. Right. So so this is the main lemma. So an NBWA rejects a word W if and only if there is an odd ranking for the run DAG of A on W. This is what we are going to show. And as you say that it was, this direction is easy to see. There is an odd ranking for G, which implies that A rejects W. Right? And now what we are going to do for this is that we are going to define an odd ranking function. So for the other direction, right? A injects W, then there exists an odd ranking function. So we are going to define such an odd ranking function. Right. So so now we have this, right? That G2n is finite and G2n plus 1 is empty. For every vertex. So, okay, so this is something we now know. What do we know? Is that for every vertex QL, which is in G, QL is removed from that GJ from some GJ where that J belongs to from 0 to 2n somewhere, because that G2n plus 1 is going to be empty. So every vertex which is there in that original DAG G, they are going to get removed at some point, right? Either in G0 or G1, G2, up to somewhere from G0 to G2n, they are going to get removed. Okay? And now I'm defining the function, which is kind of a ranking function, which we'll see. So going to define a function in the following way, that this particular a vertex QL, which appears in the tag, I will assign it a value. I will assign it a value such that that is the last sub-tag in which it was present. Clear? And anything afterwards, it's going to be removed from. Clear? So this is how I'm going to define a function, and I'll show that indeed, if G is rejecting, this is indeed an odd ranking function. That's a broad idea. Right? So that's what I want to show. Clear? So what is again this function FQL assigns you? If FQL equal to J, then it implies QL got removed from GJ, right? And this does the maximum rank that a vertex QL gets is 2n. Clear? So now I'm just defining it in this way. So if QL equal to 2i, if QL is finite in G2i, clear? If it is finite, then it should get, like, if the vertex is finite, then it's going to get removed in one of these. Like, so this is what we are doing when we are going from G2i to G2i plus 1. We are removing the finite vertices, right? So I'm exactly trying to do that. So I'm giving it some even sort of a rank here. If it gets removed from some that even numbered DAG, sub-DAG, right? And I'm giving it an odd rank. I mean, it is assigned an odd value if this is alpha free in G12 plus 1. Okay, good. So now we need to do, what we need to show is that this F is indeed a ranking. F is indeed a ranking. Okay, so what was the definition? So what were the properties of ranking? Can we try to remember? What were the, when we defined the ranking function, what were the properties that we had in any general?
It's monotonically decreasing.
Right, non-increasing. Yeah, you are right. It's monotonically non-increasing. I mean, not necessarily decreasing. I mean, can non-increasing. Sorry. Alpha vertices should have, all alpha vertices should have even rank, right? So now we see that what does this say? That alpha free vertices, so only alpha free vertices get odd rank, right? Only alpha free vertices get odd rank. So you have, for example, suppose this is the set of odd ranked vertices, right? And the alpha free vertices are like this. So this is a set of alpha free vertices, right? So only alpha free vertices get odd rank, right? And alpha vertex is all getting an even rank, right? So an alpha vertex is outside the scope of, outside this set, right? So alpha vertex is not getting an odd rank. So alpha vertices are always going to get an. So this part is clear. Okay, any question? So this is just by the definition. So just by the definition we have here, right? So from here we get it. Now we have to show the other one, which is also not very difficult, right? I mean, the whole proof is kind of quite long and we have so many like ingredients. But if you look at the individual things, they're not too difficult, like goes in steps, correct? So for two vertices, Q prime L and QL, now I'm saying that if Q prime L is reachable from QL, then f of Q prime L should be less than equal to f of QL. Clear? So this was the other condition for defining a ranking function, right? So we consider these two cases. One is that if QL is even, the other is if QL is odd. So if QL is even, then how can you show this, prove this? If FQL is even,
So if Q, oh,
it is even when I mean, so when will it be even? When is it even? It's a finite vertex. Very good. So there are finitely many vertices which are reachable from that.
so even this should also be that finitely many. Like, because, oh no, not necessary. But it will definitely start like one die before that.
So the thing is the following, that suppose there are finitely. So what I'm saying, that suppose there is this QL, right? There are finitely many such vertices which are reachable. Now, one possibility is that, like, suppose there is a Q prime L prime, which is in, I mean, so suppose there's a Q prime L prime which belongs to G, right? The original DAG. Now, it may be possible that the Q prime L prime already got removed earlier. That may be possible, right? If the Q prime L prime got removed earlier, then of course f of Q prime L prime should be less than f of Q. Okay. The other possibility is that f of Q prime, sorry, the other possibility is that Q prime L prime is also in G2I. Now, if QL is finite, then Q prime L prime is also finite in G2I, right? If QL is finite in G2I, Q prime L prime is also finite in G2I. Hence, f of Q prime L prime should be the same as f of QL because both of them are going to be removed at this stage. Okay, good. Now, can you tell me about the case where if QL is odd? It's exactly the same argument.
If in case QL is, like, since QL is not alpha free, if suppose Q prime L prime was alpha free, then it would.
Wait, so you started with like, since it is not alpha free or?
It is alpha.
Okay, because we are saying that it is alpha free.
Yeah, so since QL is alpha free, Q prime L prime can't be alpha. Can't be alpha.
Huh. So that is also alpha.
Can be, it is alpha.
That's also
So
alpha,
it should also
right?
be.
Right? So this is alpha free, then something which is reachable from there, that should also be alpha, right? So now the possibility is that either it got already removed earlier, in which case it should get some smaller rank, or it is still there in that G2I plus 1, like at that subgraph, subdat, and in that case it's going to have the same rank as Q1, right? So f of Q prime L prime is less than equal to f of Q1. Any question? Okay. Any question from the online participants? I did not write, but was it clear? Or else if it was not clear, I can try to write. So what I said was that, so when you have the Q prime L prime, there are two possibilities, that Q prime L prime was already removed earlier, already removed at an earlier stage, hence q prime l prime does not belong to G2I, right? So I'm saying that f is a ranking function for G. I mean, f is indeed a ranking function for G. That's what I'm trying to say, right? Hence, so if this is not the case, I mean, yeah, okay. So when I say G2I, well, it does not belong to some GJ or something. Let me see. Yeah. So suppose f of QL equal to J. Suppose f of QL, okay, it's even. So let's say it's some 2I. Okay, if it is even. So Q prime L prime does not belong to G2I, in which case Q prime L prime already got removed at an earlier stage. Hence, f of Q prime L prime is strictly less than f of QL. Okay, the other case is that it is there in G2I. Okay, if Q prime L prime belongs to G2I, then this is also finite because Q prime L prime is reachable from QL, which is finite. If QL is finite, Q prime L prime, which is reachable from QL, has to be finite. So in that case, f of Q prime L prime equal to f of QL. Clear? And then this other case is also exactly the same. Okay. So now we need to show that f is indeed an odd ranking. So we showed so far that f is a ranking function. Why? Because it's two conditions that alpha vertices should get even ranking and then it is monotonically non-decreasing. These two conditions we satisfy. Okay. Now we need to show that f is an odd ranking. Okay, if we started with if G is rejecting, we need to show that there exists such an odd ranking function. So we define that ranking function is, we define the function, we prove that this is indeed a ranking function. We need to show that this is indeed odd ranking. Okay. So now there is this property of the ranking function which we are going to use. What is that? That corresponding to a ranking function, right? It will get sort of like, since it is monotonically non-increasing, right? It's going to get stuck in some like rank. Every infinite path is going to get stuck in some infinite path. Okay, clear? So along every infinite path of G, there exists a vertex. Along every infinite path, there exists a vertex QL such that for all Q prime L prime, if reachable from QL, if Q prime L prime equal to f of QL. So this is something we saw earlier, right? It gets stuck in that rank. Huh? Now we show that if QL is odd. Okay. Now, suppose if it happens, then suppose for contradiction, we assume that this is even. Okay, so now can you tell me how we reach the contradiction? Can you tell me how we reach the contradiction?
If it was removed at an even stage, then that means the number of vertices reachable from it is finite. And we just got an infinite path.
Right? So nice. So what is that like? So if suppose this is even, okay, so that means that you have only finitely many such vertices which are reachable, right? If it is even, then in G2I, so what is the thing? So we are saying that, like, okay, so suppose this is for contradiction, it is G2, I mean, f of QL is even. So then what does it mean? We are saying that there is an infinite path which gets somehow like gets stuck at this even number in this case, right? So there's an infinite path, it gets stuck at this even number, right? So in G2I, you have such an infinite path. In G2I, you have such an infinite path. And why in infinite path? Because everything here, like so QL and all the successors Q prime, L prime, they have the same rank, right? They have the same rank. So all of them, then they should stay in G2I, right? All of them, they should appear in G2I. That's why they have the same rank, right? It's getting stuck there, so it cannot reduce further. So all of them have the same rank, this thing. And this is an infinite path of even ranks, even the vertices are getting even ranks, which clearly contradict with the definition that only like if it is, I mean, if it is having an even rank, it should have been finite, right? It contradicts with the fact that QL is a vertex on an infinite path. Clear? Hence, we have that yeah. So we have that F is an odd ranking. Here, F is an odd ranking. Any question? Any question? Right? So what we are saying again, for every path in G that we have, like so every path in G that we have, it gets at some point of time it gets stuck, like at some rank. And that rank in every path, that is going to be an odd rank. This is what we show. Right? It cannot be an even rank. In any path, it cannot be an even rank at which it gets stuck. Clear? So hence, we in fact, if G was rejecting, we could construct an odd ranking function. So we first showed, we defined F, we showed that this is a ranking function and it's an odd ranking function. Done? Okay. So hence, what was the whole thing that we showed that if so G is rejecting if and only if there exists an odd ranking. That run that G, which is the run that corresponding to a word input word W, that is rejecting. So we still have 15 minutes, right? So that is rejecting if and only if there exists an odd ranking function. Good. So this part is done. And now we will try to, with this, we'll try to construct an NBW given a non-deterministic Büchi word automaton A. We are going to construct a non-deterministic Büchi word automaton A prime, which accepts the complement language. And as I said, what is the broad idea? The broad idea is the following, that it will try to guess a ranking function. It will try to guess an odd ranking function. And it will also try to keep in its state space. So the state space has an odd ranking function. And also in its state space, it will have a set of states which has even rank. And that state, which has even ranks, this set of states, that should gradually vanish, right? So this is the idea. Okay. So now, hence the state space of A prime, which is a complement automaton, it is a subset of R cross the power set of the state space of Q. So what is this thing? This is like the set of all odd ranking functions. And this is the subset, right? I mean, this is the subset of those states which should sort of visit an odd rank. Like this is the subset of like even rank states with an even rank under that ranking function, and they should eventually visit some odd rank. right? And there should be a path from such states with an even rank where I will go and visit an odd rank. That's the idea. Okay, so again, this is just some definitions. So I have the notion of level. I define the notion of a level ranking here. So it's very much similar of the ranking function. So it just for every state in that given automaton Q, you have a mapping from Q to this set 0 to 2n, and there is a bottom symbol. Okay. So, and it is defined in a way such that GQ is, if GQ is odd, then Q does not belong to them. Okay. So again, only the alpha, the vertices which are not alpha vertices, only they are going to get an odd rank. Okay. So if it means that if you take the contrapositive, it means that if Q belongs to alpha, then it implies that GQ is even. Right? So alpha vertices only get even ranks. Okay. Now I say that for two level rankings G and G prime, I'm going to say that G prime covers G. Again, a definition: G prime covers G. If for all Q, comma Q prime, if GQ is, let's say, yeah, I mean, well, if it is the case that you can reach from Q on reading A to Q prime, then G prime Q prime is less than equal to GQ. So is the idea clear? Like, so I'm going from Q to Q prime, right? And I'm having a new level function G prime for Q prime, which should give it a I mean, this ranking that G prime assigns to Q prime should not be more. It should be at most what G assigned to Q. Correct. So this is what we are doing when we define the ranking function. We are going down, and at each level we have like this G of Q, and then, I mean, if it was the F, then from F, I mean, if you're going from QL to Q prime L prime, F of Q prime L prime was less than equal to F of. Here, instead of F at both the levels, I have G and the G prime, and I'm saying G prime of that Q prime is less than equal to that G of Q. Okay, so kind of like the idea is similar, like at each, so earlier we were having that level thing. Here I'm saying that it is like a level ranking. At each level, I'm coming up with a ranking function. Okay, and I'm giving this. And the idea is that I will stitch them together to get a ranking function. Okay, and all these level ranking things, I'll stitch them together to get a ranking. Okay, and then there is another definition which is like even G, which is what? It's a set of vertices that are mapped by G to an even number. Okay, so G is a function again from the set of states to this set, right? And if even G is essentially the set of states such that GQ is okay. Now each state of A prime is a pair G comma P. Okay, so as I was saying that you have like this non-deterministic Büchi word automaton, which is going to accept the complement language, complement of the given this thing. It's a pair G comma P, where what is G? So G is a level ranking function that it will kind of this automaton will guess, and P is like a subset of states, for which corresponds to that even of G, like to which G assigns an even rank. Okay, and the thing is that I would like to see this subset P to be gradually decreasing. Okay, when I encounter the empty set, that means that there are no alpha vertices there. That's what like I'm going to. I mean, it's true, like the odd vertices can also get an even rank, but I can also define my level ranking function and define, I mean, continue the run in a way such that the vertices, the alpha vertices will vanish over the time. Okay, so here is the, okay, so the level ranking function essentially remembers the states in the current level and guesses a rank for them. So it's the formal definition is like this. So you have like the state space is R cross 2 raised to Q. R is the set of all these level ranking functions. This is the subset of states. And the alpha here, the set of accepting states, is this it's a subset of this R cross this empty set. Okay. So initially I start with a level ranking function G0, and my set P is the empty set. Such that, so how am I defining G0? Such that G0 of Q equal to 2n for Q belonging to, if the Q is an initial state, then I map it to 2n. If it is not an initial state, I map it to the bottom symbol. Okay. Okay. So right now, so if I have a state which is of the form G comma P, right? We have a letter A, then I am defining the transition. So I'm defining a transition. It's like from this state G comma P, I need A, I go to another level function, level ranking, which is G prime, such that G prime covers G. And I'm keeping in this new state, I have the set of states that I'm going to and intersecting it with the even of the G prime. Okay. So it's like this sequence of alpha vertices that I do. And if this P is empty, then I sort of move the even vertices corresponding to G prime, like whatever the states that G prime maps to an even number, that I will then bring to this P. So the idea is that like whenever I'm having this some set P which has the even ranks, I would like to see them getting empty over and over again. I'd like to see them getting empty over and over. And in the level, I mean, if you remember the DAG, at some point of time, if it's a rejecting one, at some point of time, it only sees this odd set of vertices which will have the odd ranks, right? You'll see those ones which will have the odd rank. Now, corresponding to that, what I will say is that I would like to see something which has this empty on the right side over and over again. Okay, so my acceptance condition, that alpha prime, it should be of the form alpha prime should be of the form, or I can just make it like this. Okay. Now the thing is that one can show that if you have, and like I mean, we should be able to see that. Suppose if you have an accepting run in that G prime, right? So which means that so since it's a ranking function, like the property of the ranking function ensures that you are getting stuck at some particular rank, right? Now it is accepting if there exists such a run where it gets stuck at an even rank. If that happens, then this is never going to be empty, because what happens is like I'm always like going to push the even ranks in my this second component. I'm always going to push that in my second component, right? And since I'm going to have that even rank, I'm not, there will be some state which will be there in this subset, right? And it's never going to be empty, right? So this is kind of the broad intuition. It's a bit like there were too many things. I mean, too many definitions and the proof had something, but I would think that this is more or less, it's okay, right? I mean, I would say that, yeah, you can go and now look at the proof once yourself, and then if you have questions, post either in the classroom, that Google Classroom. Okay. So now the question is that how many, so this is the definition of the complement automaton. Okay. So this is the definition of the complement automaton. So we started with an initial LBW, input LBW. We are constructing a complement automaton. Okay. The complement automaton guesses these level ranking functions, or guesses a ranking function, and it also maintains a subset of states, right? Now, how many such states will be there in that complement automaton? How many states will be there? So I'm always, so what is the thing that I'm starting with some initial level function like this, right? I'm going to guess. So using these level functions, I'm actually guessing a ranking function. That's the thing. I'm actually guessing a ranking function. So I'm looking at different possible ranking functions. So for every word, I need to guess if it is rejecting in the original automaton, in the input automaton, I need to guess a ranking function corresponding to that word which is being rejected, and I have to accept this in the new automaton that I'm constructing. For another input word, I might need to guess another ranking function, right? So how many states will be there in this complement automaton? So we just looked at this, right? That this is my set of the state space. So what is the size of the state space?
So the size of R is the number of functions from
Yeah,
n to n.
correct. Yeah.
This is like n to the 2n.
Or is it the other way around, 2n raised to n? But right, because right, so it's more or less like, so you see that this is what we get here, the size of the state space. It's like this, 2n plus 1 raised to n, and I also did not write like multiplied by 2 raised to n. Now this is of the order 2 raised to n log n, right? Because you have n raised to n. This is like 2 raised to n log n. Clear? And you can just take log. N raised to n is like n log n, and then if you again take the exponentiation, it's like 2 raised to n log n. Right? Now, okay, so we are almost out of time. So when you do, let's say you are given an NFA, right? You are trying to construct, like when I say NFA, I mean over finite words, and you are trying to construct a complement automaton. So what kind of blow up you would get if you have n states in the input automaton?
And then we will determine
Sure.
then complement.
NFA you will determine it, and
Then complement the.
yeah.
So it's exponential, you know.
Yeah, so 2 raised to n.
Yeah.
Right? And here we are getting 2 raised to
And
n log n. So in the case of NFA, we usually get, like, if you are doing the complementation, right? So you start with n states, you construct a DFA and complement. So this is like 2 raised to n. In case of NBA, I start with an n states, the complementation procedure is giving me 2 raised to n log n disorder. Right? Something like this. So now I posted some notes and also I discussed in the last lecture that if I say I'm smart enough, I have a better algorithm than this, I don't need, like, so this is the standard, like what you did in FA to DFA, it was a subset construction. Now, if I claim that I have a better construction which does not require that exponential blow up, will you trust me? You won't trust me. Why?
Because there are languages for which the minimum size of the complement NFA is 2 to 9.
Correct. Right? So because you can show that, I mean, you can indeed show, like, so the one that I posted was for the determinization construction, which was part of this. But you can in fact like also show, I mean, that also something you can search, that when you are taking the complementation, that also requires, right? I mean, it's not exactly what I posted, what I'm asking, it's not exactly the same. But what I'm saying is that, like, there exists some family of NFA such that their complement will have like exponentially many states. And now in the next lecture, what we are going to show is that in the case of NBA, this is tight in the sense that there exists a family of NBA, non-deterministic Büchi word automata, such that, so I'll just look at the statement of the theorem such that the language is recognized by NBW with n plus 1 states, but every NBW which recognizes the complement language will have at least n factorial states. It has n factorial states, right? So this still has some gap. Like, I mean, we started with some 2n plus 1 raised to n, right? Yeah, 2n plus 1 raised to n. And here I am saying n factorial. But this is what we'll do in the class. But there are, if you look at the chapter, there are references to other words which kind of try to tighten the gap. Okay, so tighten the upper bound as well as tighten the lower bound. So these are things you should try to look yourself. I mean, and at least look at some of the references yourself and see the paper. If you find something interesting, you can post it on the Google Classroom for everyone else and things like that. And we are going to have some seminars also, as I mentioned, as part of the grading and all. So this is, I mean, you can also try to, it's not necessary that in a 300 level course, I am going to assign the papers. I can assign some of them, and there are just few of you, but I mean, if you also come up with some paper which you think is interesting, and we can discuss and you can also present that. Okay, so what I would suggest is that now you can go through this for this complementation procedure from that chapter and try to take a look at least the introduction of the references which are there, right? I mean, just see what are the results that those references they do. Okay, good. So I will stop the recording here.